Hello and welcome to my 13th lecture in operating system development. And today I will discuss a very fascinating topic. I'll be discussing user space processes and scheduling them and different things pertaining to multitasking. This video is highly related to the next one that I'll make. I think you could even think of those two videos that'll come out, this one and the next one, as me just splitting a topic in half, just making a part 1 and part 2, because the next one will be about threads. It will be about different things that generally arise when you have preemption, you have multitasking, and you have different processes, things such as the critical section problem or deadlocks. So there will be even more considerations related to that in the next video. And this is just a general introduction to processes, to scheduling processes, and how we can generally do things like that in an operating system. So first, well, the term user space is generally an abstract term that refers to the part of the operating system that the user is going to be interacting with, right? So we had the bootloader, which was responsible for setting up an environment for the kernel and loading it. Then the kernel, is actually the core part of the operating system, which is managing all of those different resources and such. And it actually makes processes, the user space process, be able to communicate with the hardware or obtain some services through the kernel, right? And then you have the user space. But obviously there are different ways to design that. The relationship between the kernel and the user space is going to be entirely different in something like a monolithic or a microkernel. But the general idea, right, is that the user space is what the user is going to be actually interacting with. And this abstract term is usually given a concrete meaning in terms of an actual architecture or a set of hardware. And if it comes to x86, there's something called the ring protection system, which I've already briefly mentioned, but the idea is that you have 4 essential rings, and thus they are controlled by 2 bits. And that's ring 0, ring 1, ring 2, and ring 3. So ring 0 is also called the kernel ring, and this is the CPU mode in which, well, it's not really proper to call it the CPU mode, but it is a type of CPU operation in which it will pretty much allow you to do any instruction. So you can do absolutely anything that you want with the CPU. That's ring 0. So obviously this is the mode you generally want your kernel to operate in, and thus it's called the kernel ring. And you have rings 1 and 2, which generally should, have a bit more, should have some more permissions, but not as much as the kernel. So it works very well for things such as drivers and servers. Especially in things like like microkernels or hybrid kernels. And then you have ring 3, which is very unambiguously just the user space. The ring 3 is a very limited mode in the sense that it can't do a lot of operations, but that's a good thing, right? Because you're going to be able to redirect anything that could actually mess with your hardware to the kernel. And well, the question rises, a very obvious question, like how do you do that? And this is something that I believe I have roughly explained in the very first video in this series, and that is something called a system call. So you have the user space, and you have the user space processes, and you have the kernel itself. And whenever a user space process wants to do something, it says to the kernel, hey, I want to do this and this. And the kernel can obviously either reject or accept that request. If it accepts it, then it provides that service to the user space process. So that's the idea of a system call. A ring 3, part of, just ring 3 code does this sort of call to the kernel, which can execute ring 0 code in order for it to decide whether to do some operation rather than do it in ring 0. So if it comes to the actual details of getting into ring 3, I don't think that's really necessary to cover here. I mean, obviously you have things like the task state segment and everything that you have to set up, but it's, they're just tricks for getting to ring 3. It's not that difficult of a thing to do. You can easily find that. In this video, I'll focus more on the general abstraction of the process and the way you deal with those, because I find that to be much more valuable for a lecture rather than just dry documentation or code that does a specific thing. But if it comes to system calls, I mean, that's obviously a thing that is worth talking about, because, like, how would you even design that? And well, it's the way that it is done usually is you have some interrupt. This interrupt is usually called a trap. And the idea of system calls and the way they're implemented is that you choose a specific value that is usually hexadecimal 80. So you have the interrupt 0x80. And you have an entry in the IDT and everything. And the process, which is currently running in ring 3, some code which is running in the Userspace, it is allowed to, call this interrupt, and based on the values that are contained in the registers, the CPU, and the kernel is going to know what sort of thing it should execute, right? So some register, like EAX, is going to contain the instruction, like what system call should actually be done, right? So that's the identification of the system call. Obviously some known system calls are the first 4 system calls of Unix systems, which are used for managing the virtual file system. So things like open, close, read, write, I probably didn't give them in the right order, but those are like the first 4 system calls of a typical Unix system. And I say Unix for a reason, and it's because, obviously you can implement the system however you want. You can say, oh, EAX, this and this and this are going to be those, and the EBX is going to hold like some parameter, like if it's, I don't know, writing to a file, right? Then EBX can have the file pointer, ECX could have, I don't know, the actual, the pointer to where the string that you want to write is contained, right? And honestly, obviously you can design your operating system and your system calls in any way that you desire. But the problem is going to be compliant with anything, right? So the main point of your operating system, a huge turning point, is going to be when you finally have a relatively quote-unquote complete operating system, in the sense that you already have a lot of things. You can manage all the different resources, and you have you can compile for your operating system. At that point, you're going to be mainly concerned with porting user software, right? So obviously there is some software available that a user would expect on an operating system, and you're going to be porting that onto your operating system. If you don't make system calls which are compliant with anything, that's going to make the process of porting anything an absolute nightmare. So what I would recommend is POSIX compliance. So there's this norm, IEEE 1003.1, usually known as POSIX, or the Portable Operating System Interface for Unix, which is contained in this norm called the SUS, or the Single Unix Specification. and it dictates the all the different system calls. Or you could just simply look at the Linux kernel or other Unix kernels and generally be inspired by those. And this will make it so that when you try porting things and it will try calling some system call with some arguments contained in the CPU registers, your operating system will be fully compatible with that. So that's the general idea of Ring 3, the user space, and how user space processes communicate with syscalls. But what even are processes, and well, how can you actually create them? And the two terms that are confused very often are a program and a process, right? So a program is this static thing. It's just a bunch of code, a bunch of CPU instructions, usually contained in some memory, like for example, a hard disk. So that's a computer program. And it only becomes a process when it actually goes into the operating system. So the thing is, a process is an active unit that has to be actively managed by the operating system. So the operating system has to know the state of a process. The process can actually be running. The instructions can be executed. So this passive component is the program, and the active component that the operating system has to actively care about and manage is the process. And in one of my videos, I think it was the one about loading the kernel, I have talked about ELF, the executable and linkable format. So you obviously shouldn't use flat binaries, which are just files, that have a bunch of instructions one after the other without, any sort of header or anything. It provides, flat binaries don't provide, well, I can't even say that they provide too little. They provide no information whatsoever about the program that are going to be running. So obviously you should use some sort of format like ELF that I've already covered. And ultimately you're going to have also just a set of instructions, but at least you know something about it. And well, you could simply, you have the RIP, the register, which contains the instruction pointer. And you can set the instruction pointer to any memory address, and then the CPU is going to start executing the instructions which are placed at that address. And you can obviously just do that after loading something like an ELF file. So you load an ELF file, you'll have all the instructions, and you could simply set the RIP to where you have loaded the instructions, then it will start executing them, and congrats, you're running a program on your operating system. And well, you could just do that in Ring 3 and you're running a Userspace program, but you could sort of call that a process, but the problem with that is just how you shouldn't just use flat binaries. You shouldn't just use processes in a pure form of, hey, I just have a list of instructions and I'm going to run that, because that is going to be ridiculously difficult, if not impossible, to manage. So obviously a process needs to contain some additional information, or the abstraction of a process that you're going to contain in your operating system. It needs to have some sort of additional information, and that is usually something which is called the process control block, or PCB. Right, so you have a process control block. And it is going to contain, different sorts of information that would be useful. So what could be useful to know about a process? Well, of course, you could want the information about, its sort of stack address, because obviously you should give any process in your operating system a stack. Its own stack that it can sort of push and pop data from. Well, you could, for example, have a list of memory addresses that it owns. I think, well, it's not that I think, that's a vital part of a process to have something called a context. This is probably one of the most important things, because the context is something that will allow us to later perform any sort of multitasking, preemptive multitasking, which I'll be talking about in this video. So the context is something that will allow us to know where a process has completed its work by that moment. And in reality, this is usually just this values of all the different registers at the time that the process was stopped or its CPU time was preemptively taken. And it's called the context for a good reason, because it will allow us to sort of get the context of where we should execute the process from. It will make more sense in the later part of the video. So that obviously another important information would, for example, be the state. And there is, different things that it could contain in a process control block. But the idea, the key takeaway is that you definitely shouldn't just execute pure instructions in ring 3 and call that a manageable process, because, well, usually you should include a whole process abstraction in your operating system, which is going to contain different things related to the process, because that is going to make this active unit that you're going to have to manage as the operating system actually manageable. Right? So if it comes to, well, initiating processes, obviously also in this process control block, and you obviously need some PID or process ID. I think that's also relatively clear, because you need some unique way to identify the process if you, for example, later want to kill it, or, well, perform any operation on it for that matter. If you're going to be communicating with a process, or a processor going to be doing IPC, inter-process communication, they're obviously going to have to, well, but they don't actually always need to know their PIDs if you have a buffer, and but it doesn't matter. So that's the general idea. And if it comes to the state of a process, but that's because processes, as was active unit, they're going to have a relatively set out path of what we're going to do for their lifetime, and they need to have proper states in order for the operating system to know what it has to do with them. And obviously a process starts as new, and this is going to be a typical 5-state diagram of a process. So at the beginning, a process is obviously new, so we're still going to be allocating different sort of resources to it and such. And then once the only resource that it's missing is CPU time, we're going to tag it as ready. So at this point, the process, the only thing that it is missing is some CPU time. So it's ready to execute. It just has to be given CPU time, in the sense that you actually have to set the instruction pointer to the beginning of the code of this process, so that it actually starts executing. But it's entirely ready for that. A process can obviously be running, so you can actually be executing its code at a given moment. It could be waiting. Or, well, at the very end, it's obviously going to be completed. So if it comes to going from ready to running, as we've said, that means that it has finally been allocated CPU time, right? And its code is actually going to be running. So This is CPU allocation. So we allocated some CPU time. And then after a given amount of time, a system set amount of time, depending on the scheduling algorithm that you use, you would have something called a preemption. The preemption is going to take away CPU time, and it will make the running process go back to the queue of ready processes. And at any point, a process can go from a running to waiting, and then at some point it could go from waiting to ready. So this scenario, for example, occurs in a situation in which you have a process and, for example, it needs to wait for some I/O operation. So, for example, let's say that a program wants to print something. Well, it has to wait for the printer to actually perform all of the printing. And thus, it can go into a waiting process. It's, for example, going to yield CPU time. And then once everything has been done, and thus the process could be running again, it gets back to the ready queue. And as it's running, at some point, we might get an exit system call or something of a similar kind, which is simply going to make the process completed. So that's a standard 5-state diagram. You have a new process, then it goes into the ready queue once it only needs to be allocated CPU time. If it is allocated CPU time, but it's obviously running, since it can't be running forever in something like a multitasking operating system. Well, it could, but we usually do not want that. There will be a preemption at some point, which will make it go back to its ready state. Alternatively, maybe it is going to wait for something like an I/O operation that's going to be waiting, and then it's going to be ready again once it about has completed. And let's say it's running again, and then it exits, and thus the process is completed. So that's those are the general 5 states. Entering a new process is a thing that the operating system has to manage, and exactly it's a part which is the scheduler, but there are actually 3 types of scheduler. And the term scheduler is not usually used for, I mean, it is used, but usually when you use the word scheduler by itself, when people use that word, they mean something called a short-term scheduler. But actually I have 3 kinds of schedulers that I'll sort of elaborate on later in this video. But well, you have a long-term scheduler, which is actually going to decide that the process is actually going to be in the operating system. And you have a short-term scheduler, which is going to actually be responsible for allocating some CPU time to a process from a queue, or doing some preemption in order for the process to go back to ready. So that's a short-term scheduler, which is usually just referred to as the scheduler. That's usually what people mean when they say scheduler. And you also, in many operating systems, you have something called a midterm scheduler. And it decides whether the operating system, whether the process should be moved into the swap region on the disk or not, right? So when you have paging, when you have a swap partition, the midterm scheduler is going to decide that. And that's very well visible on something called the extended Unix state diagram. If someone is interested, I highly recommend looking up a Unix process state diagram, because it contains a few more states, such as, for example, the zombie state, where you have a child process whose parent is dead, but it left and sort of information about it. So part of the operating system still sort of thinks that's a thing. That's a zombie process. So there are some interesting things, and a vital part of Unix states is also that you can have, like, for example, ready or ready in the swap region, right? And the midterm scheduler would have to swap that in order for the process to be running. And obviously a process can be running in the swap region. You only really want to run code at any given moment from the random access memory, not really from a hard disk or any other media storage device, which would have a swap partition. Yeah, so that's the idea of the different states of processes that are going to find themselves in, and obviously the operating system is responsible for making all the schedulers, with arguably the most vital one being the short-term scheduler over here, which is going to actively decide which processes from the ready queue are going to be allocated CPU time, when that CPU time is going to be taken from them by the way of preemption. So obviously this is also sort of simplified diagram, especially if you have something like a multi-processor operating system. So for example, if your CPU has multiple cores, then you have as many running processes. You can have maximally as many processes as there are CPUs, because here in this diagram, if you have one CPU, you obviously can have only one process running at a time. If you have n CPUs, you can have at most n running processes. You can have an infinite amount of ready processes in theory, right? You can have as many of them, and they could be theoretically allocated time by the short-term scheduler. That's independent of the amount of CPUs. Yeah. So that's the general idea. And you're going to be creating a process by loading some program, right? So you have some program, and it should be saved in proper formats such as ELF. Alternatively, if you want, I don't know, portable executable, I guess that's fine as well. So you have that executable file, and you read the header and everything, and what you end up with is just a bunch of instructions. Again, if you want some specific information about the ELF format, that was in a video I made about loading the kernel, because I talked about loading the kernel from an ELF file. Except since now I've also talked about file systems, you could actually have the ELF file in a proper file system. You could contain it within like FAT32 or something. You could just have a FAT32 partition, but you hold your, for example, program on, or any other file system for that matter, if you implemented that. So you have this file, you have this program, and you sort of parse it, and you end up with a set of instructions. And this set of instructions, it begins at some point. And obviously, the sort of process instruction should be contained within the abstraction of a process. The abstraction of a process would also contain the process control block with the information. Well, somewhere in this process abstraction that you have in your operating system, you should have, it could be a struct or something, process, right? And you obviously need the base pointer of where your program actually begins, right? So the beginning of your program in memory is always something you should contain. And then once you fill out the other data, and if you have the base address of where the code actually begins that you have to execute, and you have all the different information of a process, that its state is new and all that, and you have default context, for example, all filled with zeros or whatever. Well, that's usually not a good idea. You just save the context that the CPU was previously in, but it doesn't matter for now. And once you have that, well, congrats, you sort of have a process. But usually it's not that all of the processes are instantiated linearly by themselves, because that's quite inoptimal to make this whole process abstraction each time sort of from the beginning. And that's why a process abstraction should also contain information about children and parents, right? So you create this sort of process tree, and the motivation for this process tree is that the sort of Unix solution to creating new processes and making new processes run is something called the fork primitive, right? So what do you do with this Unix solution is to use fork, which is going to copy all the contents of an already existing a process in memory and just create a new one that sort of stems from it, and then only like override the one that you actually create. So that's the Unix approach to sort of creating new processes. And this very easily sort of makes us imagine a sort of hierarchy. So it obviously could have something like a root process, and this process could have some children. And then, you know, you could instantiate some new process by, for example, forking this, and you can make it a child. So the process abstraction in your operating system would also contain, for example, the information about the children and parents of a given process. Well, not parents, the parent of a given process. So this sort of creates a process tree where, you know, processes create child processes, and those child processes have a parent process. Yeah, so you in order to create this process, everything you need for this process to fill all the data in your process abstraction to some default values, and obviously you have this instruction pointer, sort of, well, just the pointer to where your code is actually going to begin of a process that you have to execute. And yeah, so that's generally it. Well, and now comes a sort of a fun part, because well, you have those processes, but from the way I described it, it seems really easy to manage one process, or maybe one process at a time, because, well, if you have sort of instruction pointer, then you can simply have a scheduler, quote unquote, as just a function, which, you know, would set the current RIP, the register with the instruction pointer, to whatever the base pointer of the code of your processes, and it would just start executing that. And then you could do another process, right? And like that. So it's easy to imagine sort of one process at a time, or a monotasking operating system, right? So even in monotasking operating systems, there are sort of different ways to schedule. And well, what is scheduling? Well, scheduling is, or short-term scheduling is just deciding when CPU time is going to be given to a given process, or when it's going to be, for example, taken away. So the allocation of CPU time is performed by the short-term scheduler. And as I've previously mentioned, you also have a midterm scheduler, which is going to decide when processes are going to get in the swap region or out of the swap region back into the random access memory. And the long-term scheduler, which is going to decide when jobs are going to enter the operating system. So the short-term scheduler, if we're going to make a monotasking operating system, because I think it's really clear how you could do a monotasking operating system. If you have those process abstractions, right, you would just you know, you have a list of all the processes in the operating systems, all of them are, for example, this struct, the process struct, and you would just take the instruction pointer value and you would set the RIP to that. The process would complete itself. Once it is completed, you know, you would take the other process, you would set the RIP to that, it would complete itself, and so on and so on. And that's sort of how monotasking operating systems would work. And there's still a couple of approaches to scheduling those. Well, I guess the most trivial one would be FCFS, or first come, first serve. So let's say we first receive a process P1, and then we get P3, then we get P2, and then we get P4. Well, the idea of first come, first serve is trivial. It's exactly as the name suggests. We simply execute the processes in the order that they are given to us. So we would first execute P1, then we would execute P3, then we would execute P2, and at the end we would execute P4. So that's how first come first serve works. I think that's relatively easy to understand. But if we have some additional information, for example, about how long a process is going to execute, and for example, roughly estimate that by the amount of code that it has, if we have some estimate of time, for example, let's say this would take 20 nanoseconds, 30 nanoseconds, I don't know, 10 nanoseconds, and then 15 nanoseconds. Then, well, first come, first serve is not going to care about that, but we could use something like SJF, shortest job first. And I guess the name suggests what we're going to do here. We're going to take the shortest one, which would be P2, and then P4. Then we would take P1, and we would execute P3 at the end. And you could also do priorities, right? So we could say that this process has some priority, and this has some priority, and then based off of their priority, you would execute one before or after the other. I think that's relatively intuitive. But the thing about priorities, well, the viewer has probably encountered this, but if they've been messing with operating systems, but the tendency is that when you have a lower numerical value, that actually refers to a higher priority. So, for example, 1 is a higher priority than 2. So actually, the lower numerical value is going to mean a higher priority, usually in operating systems. But it's sort of a Unix norm, and the norm in generally operating systems. And I'd say computer science in general. So multitasking is easy. But what about actually multitasking? What about scheduling in such a way that we can smartly manage multiple processes, right? So we could easily imagine how you can execute one process after the other, one just completes, and so on. But how do we make it so that we use, all the process abstractions that we have actually created, and especially one point, the context? How can we actually use that to get this illusion that we get in our operating systems of multitasking, right? Because we're aware that if we only have like one CPU, then it is only going to execute one instruction at any given moment. And yet, I can have, for example, some recording software open, and I can have a web browser open, and I can use them, quote-unquote, simultaneously, and I will get the illusion that it is so, that I'm actually multitasking, or that the operating system is multitasking. And, well, the fundamental idea behind how you could do that is that you give each process a given slice of time, or a quant of time, how it's sometimes referred to in literature. So if I have some processes, F1, why am I calling F? P1, P2, and P3, then the idea is that I would give P1, let's say, 20 nanoseconds, and then I would give P2 20 nanoseconds, P3 20 nanoseconds. The way it's usually written in literature is you write a sum of the previous values, so I'll write it as so as well. That's a potential approach, right? That you give each and single one something like 20 nanoseconds, and you sort of do them cyclically. So you do P1, P2, P3, P1, P2, P3, and so on. If a new if something new enters the system, the operating system, there's a new task introduced by the long-term scheduler, then it just gets pushed to the back of this usually. So you just perform this, right? And if you do it in exactly this fashion, this is something called a round-robin scheduler, often abbreviated to RR. So it's a round-robin scheduler. You could obviously, play around with this and, for example, introduce priorities, right? And based on the priority, you could, for example, give it less or more CPU time. But I think that there are just a couple problems that arise from the very thought of doing something like this. Because it's easy to say, hey, let's give us 20 nanoseconds, 20 nanoseconds, and so on. But there are actually two problems with this. Well, how is our operating system going to, actively determine that a given amount of time has passed? So we obviously need some sort of clock. And, the second problem is, we know that we can sort of execute a process by just setting the instruction pointer to a thing, and start executing that code in ring 3, and we can say that this process is running in Userspace. So that's simple enough. But if I just stop executing it after something like 20 nanoseconds, and I do 2 and 3, then 1, if I start executing it again, it'll start from the exact same point as it did. So I'll be under the impression that none of the processes are actually doing anything. They're actually all in the sort of starting position, they're going back to the starting position. And you obviously need some way around those two problems. And the idea is something called context switching. So context switching in and of itself is the idea that whenever you do a preemption, which is just taking away CPU time, so some event happens, this event, for example, being an interrupt that says, hey, this is no more, we're actually not going to care about this anymore. Well, not that we're not going to care about this, but we're not going to execute the process that was being executed anymore. So there's some sort of preemption, and thus the control is given back to the scheduler. And the scheduler, what it does is, as I've said, in the process control block of P1, or any process for that matter, there should be something called a context. And the idea is that you would, for example, take all the values of, what you would do is you would take all the values of the registers, and you would simply store the values of all the different registers at a point of preemption. So you take all those values that P1 had, and you save it in a context. So this has some sort of context, and you go ahead and save it. And then we execute P2, right? And we sort of do the exact same thing. And we do the same exact thing with P3. So what we simply do is we save all the different values of all the registers, including the instruction pointer register. So we will know which point is left off at. But also, if it was doing any other operation with any other register, that is all going to be saved. So we're going to be able to retrieve the exact state that the process was in. So we'll save this, all this information to the context, and once we want to do P1 again, once the scheduler has decided this, that it will be performed again, what it will do is it will take this context, it will start P1 with this context. And this idea is called context switching. So whenever we actually have a change between one process and another in a multitasking operating system, we have to perform a context switch so that the current process knows which point it left off at last time. And this is simply done by, since we stored all the values of registers at a given point, we're simply going to set those registers back to the values that we stored in the context. And this allows us to have a multitasking operating system. But I still haven't covered sort of the second problem, and that was the time, right? So you need some sort of clock. So one potential solution is obviously using the PIT, or the programmable interrupt timer. Well, there are a lot of sort of clocks that your operating system could use, but PIT is one that's relatively easy to use because it's easy to change its frequency. It's sort of easy to change how frequently it should fire, and whenever it fires, it's pretty easy to manage because it's simply RQ0. So you would have to write a handler for RQ0, and that'll allow you to do anything you want at a given frequency, which will give you some sense of time, right? So one approach that you could theoretically do, but it is highly not recommended, is that you could make the RQ0 like interrupt service routine basically your scheduler, in the sense that this interrupt RQ0 of the programmable I never remember it's a programmable interval timer or the programmable, I think it's the programmable interval timer, right? Well, the PIT. You have so basically what you can say is my preemption, this event that I said that is going to do this preemption, is going to say, okay, no more of you. I'm going to store your context and set the current instruction pointer to the one of the next process, which is in the queue. You can make the preemption event to be the RQ0, which sort of intuitively makes sense initially, because it's something that happens at a given frequency, and you can it's something that seems very good for preemption, especially since it's an ISR, and so if you have a user space process, you can still through the interrupt easily make the kernel, because the scheduler is going to be a part of a kernel. Then you have a user space process, and there's an interrupt, and obviously you can do something in ring 0 at that point in order to do something with the process management. So it seems like a very good idea at first, but actually making your schedule dependent on some sort of interrupt is not really a good idea. If you do want to do that, well, you could just push all the register values like you do in a lot of interrupt service routines if you expect them to change anything, because the idea of an interrupt in general is that you have some sort of request and you handle it, but then after you handle it, you want to go back to what the CPU was doing. So obviously, what you usually do is you push all of the registers anyway onto the stack that might be modified by the interrupt service routine, so that once it is done, you pop back all the different registers. You pop the values from the stack back to the registers, so you know that you haven't changed anything, and the CPU can go back to whatever it was doing, and it's uninfluenced by the interrupt service routine. So since you're pushing all the values, you could simply, if you're calling some external function, which is, for example, in C, well, then you could just then take all the values that were pushed, and just take that and store it into the context of some given process, and it's not really difficult to do. But it is not recommended to do it that way. So it's way better to, well, if you're going to use the PIT, I would just recommend the either increase some sort of counter or whatever, or you can use some different clocks, such as the HBED, the high precision event timer. Well, either way, you're going to have to use some sort of clock. You could use the programmable interval timer. And then you would have something else stringing time, and for example, one potential solution is just yielding, which is, you have a process, and it's up to that process to yield CPU time. So after some time elapsed, it is the responsibility of the process. Maybe even if it's not in the code of a process, you could just actually add it, so that the process after some elapsed amount of time yields back the CPU time. In that way, it's good to make the preemption non-entirely based of the interrupt. So that's the general idea of multitasking in the simplest possible sort of scheduling algorithm, which is the round robin, or round robin with priorities. You could implement that, right? which is just like you keep on changing each given amount of time, and you start with context, all the values of the registers, and you put the values in the register back from the context once you want to do everything again. And that's basically the job of your short-term scheduler. So that's a round robin, and it is very similar to, because when you have multitasking sort of scheduling algorithms, they're always like very inspired by what previously functioned monotasking operating systems. So round robin is sort of very similar to FCFS, first come first serve. I think that's pretty easy to see. You do all the processes in the order that they're given to you. But as one might suspect, that's not usually the optimal approach. So what sort of most modern operating systems do is they use some sort of variety of something called the multi-level feedback queue. Or MLFQ for short. So, the idea of a multi-level feedback queue is that you imagine there being, well, you don't even have to imagine, you just implement it. You have some sort of queue data structure. You obviously have a sort of LIFO, right? And you imagine the different queues. And let's say I have one queue, I have another queue, I have another queue, which are often also just referred to as the dynamic priorities, or simply priorities sometimes, for different processes. In the sort of most typical multi-level feedback queue, you consider for all the processes to, let's say I have processes, right, P1, P2, P3. You generally consider all the processes to start at the queue with the highest priority. They have a queue with the highest priority, which can be 1 or 0. It's both sort of function and different operating systems. But what matters and what is the norm is that the lower numerical value refers to the higher priority. So you have processes like that, and if two processes, so they all start in this queue, and if two processes have an equal priority, or well, if any sort of processes, if any pair of processes, any sort of amount of processes has the same priority, then you execute them in a round robin fashion, which, because of the fact that we're going to decrease the queues, well, not decrease the queues, move the process into queues of a lower priority, it's basically like first come, first serve. So I have P1, P2, and P3, which were given to me in this order, and basically what I can say is, okay, so what I'm going to start doing is I'm going to start executing P1. So let's assume the quant of my time that I'm going to be performing preemption after is 20 nanoseconds or something like that. So I do this for 20 nanoseconds, and what happens is this process of mine is going to move to a queue of lower priority. So it's going to move. So now I'm going to have a queue containing the processes P2 and P3. And well, the next rule of a multi-level feedback queue is that, you know, if some process has a priority higher than the other one, then you execute the one with the higher priority. The way it is phrased like that is because sometimes historically they were just stored linearly with, you know, just a piece of information of which queue it sort of belongs to. And that's still sort of done, right? Like you obviously have those queues, but really only usually the scheduler is sort of, I mean, it's a business scheduler anyway, but like what I'm saying is, you know, you have some list of processes and, you know, you check for, like, which ones are existing and you check for sort of queue, and then it's sort of like easier to manage. But the idea is, right, so you have P1 and it just sort of goes to a queue if this lower priority, and if a process has a lower priority than, if some process has a higher priority than some other process, but the one with a higher priority is the one which is going to be executed. So again, over here we would execute P2 and would move here, P3 would move here, and then P1 would move here, P2 would move here, and P3 would move here. And someone might say, well, what sort of sense does this algorithm actually make? It just seems like round robin. And the reason it is not round robin, because it does just seem like it from this description. I mean, if you have those three processes, the execution is going to be exactly the same. It's going to be identical to round robin, right? You have, now we're going to do P2, P3, then P1 is going to move down, then P2, P3, and then you're going to be doing the ones in the third queue, and it's going to behave exactly like round robin. There are two things which one must consider, which immediately make the multi-level feedback queue sort of more appealing. And the first thing is you have to remember that processes don't work in a way that you start an operating system, you have all the different processes, and you just schedule all of them at the very beginning, right? No, processes are actively, you know, sort of run, and they're initiated by the user of the operating system, and this happens during the time that the operating system works. So, for example, obviously some user might launch some sort of software after an hour, or they might launch a little program that is just supposed to calculate something, you know, 2 hours into the working of the operating system, and so on, or a video game after 3 hours. And this makes it so, as I said, round robin was highly inspired by FCFS, first come, first serve. And the other sort of scheduling algorithm that was really popular in the days of multitasking operating system was, you know, shorter job first, or SJF, where we sort of estimated, or in some situations had, you know, a quite accurate amount of time that a process would need in order to execute. And obviously, in modern operating systems, the moment of completion is usually determined by the user. Like, that's how most modern user software work. That, you know, I have, for example, some recording software, and it runs until the moment that I click that little button in order to turn on the recording software. And because of that, you can never estimate the amount of time that it's going to take, because it's obviously going to be dependent on the user. So the mechanism you could use instead is, the longer the user is running it, the less CPU time I can give it. And initially, for some people, this seems counterintuitive. Wait a second, if I'm using it for a long time, it should probably receive more CPU time, but this is not true. Because you have to remember that a lot of processes, there are going to be a lot of processor threads that are doing like very tiny calculations, and they're going to like execute relatively fast. And generally, when you're starting a process, it should receive more CPU time than the ones that are running for a long amount of time. Obviously, we don't want the quality of software running just continuously decreasing as we run, because it is, intuitively quite also important to sort of have for the programs that we run for a long time. I obviously don't want them to work in a way that is way worse after 2 hours than after we booted the program. And so it is inspired by a storage job first, and as you can see, if we have those programs which they've been running for a long time, they would be in the third queue, at least. Well, not necessarily, but I will explain it in a second. And then when there's a new process to enter the system, it is going to start in the queue of the highest priority, and it's going to be executed sort of the fastest. And this makes it so that processes that don't last very long, they're given CPU time quite quick, so that they don't starve, right? So this is a very sort of noticeable difference between the MLF queue and round robin, which is very useful in practice. And the other thing, because well, when I was talking about this, we don't want a program to work in a worse condition than after we started running it. If it did work that way, then a user would obviously think to themselves, I should probably turn off my computer program once in a while and then boot it up again so that it works as well as it did initially. And it would be that way, but fortunately just a computer can do that. A computer can, and that's the way that LFQServe works, with the sort of mechanism that is called boosting. So the idea of boosting is that in order to not have this continuous decline of all the different priorities, you're obviously going to have some conditions under which processes are going to go back up to a higher priority queue. So there's generally a rule that after some given time, which is defined somewhere in the scheduler, all the processes should go back up to highest priority. So after some time, all the different processes are going to be working, quote unquote, like brand new. And that obviously makes a lot of sense. You might also define, because those are, as I said, something called dynamic priorities, but you can also just define static priorities. Obviously, some processes could be less important than the other. And, there are, for example, Unix programs such as nice in order to sort of configure all those things. And, you could have systems processes which could be more relevant, and, each process individually, depending on its importance, it could, for example, get boosted, for example, one queue up a good amount of after a given amount of time, based, for example, on its priority. So that's the multi-level feedback queue. There's just a lot of different parameters, different numerical values that you can generally play around in order to see what ends up being the most optimal. But generally, this approach of multiple queues, this idea of boosting, and this inspiration by shortest job first, it is generally considered to be a good modern multitasking scheduler. And well, obviously, when you're switching from one process to another, nothing changes in comparison to a round robin sense, but you still have the same sort of context switch mechanism. So far I have sort of assumed that you have one CPU. But nowadays, people usually have multiple CPUs. Even if they don't have, what they would consider multiple CPUs on their motherboard, you have to remember that CPUs have cores. And fundamentally, there isn't really much of a difference from the perspective of an operating system, just in general, between a core and just a separate CPU. To sort of oversimplify, but not even that much, cores are just different CPUs, right? So, you know, whenever you consider like 8 cores, you imagine that those being 8 CPUs, and they sort of are. They can perform, each of them could, you know, they have the entire ability to, you know, execute some instruction set, and the 8 of them could be processing different instructions independently of each other. And, you know, it's good to sort of utilize that. It's good to use those CPU cores in an operating system. And because of that, you obviously can have multi-core or sort of multiprocessor, to generalize, you have multiprocessor scheduling. And well, in practice, you often have to communicate like with the ACPI and everything in order to get the information about the different CPUs and actually, you know, perform operations on them. But what I think matters is sort of the design of how you're going to handle giving out the different instructions of different processes to the CPUs. And there are 2 main approaches to actually doing that, because you can consider all the different CPUs homogeneous. And I have no idea if I spelled that right. I probably should have checked that. I have no idea if it's just like that, but that looks weird, so I'll just assume it's something like this. So the last time I said that word, it was in Polish, so yeah, but you're gonna have homogeneous CPUs, and that basically means that you assume for all of your functions to be precisely identical. And a sort of solution that stems from that is something called SMP, or symmetric multiprocessing. So you have all the different CPUs, which are sort of equal to each other, or identical. And you know, they're all sort of given a copy of a scheduler, and they're all scheduling the processes by themselves. So you have some processes, and you know, P1 could go to this CPU, P2 could go to this CPU, P3 could go to this CPU, at least for a given quant of time. So you generally consider them to be equal, and you know, they all sort of have a scheduler, and they just take any sort of process that was ready to run. And you know, they see, oh, this a given CPU, you know, they're all sort of independent. It sees, oh, this process is ready, I'll take it, and then it's not ready anymore. The other CPU knows of this, well, and it's going to be running on a given CPU. But alternatively, you could consider all the CPUs to be heterogeneous, which means that you assume for them to have different functionality, for them to be functionally different. And this leads to another sort of solution called AMP, or asymmetric multiprocessing. And the idea of asymmetric multiprocessing is that you have those CPUs, and you, for example, consider some CPU to be the master, and then the other CPUs would be slaves. So you have this sort of master-slave hierarchy in asymmetric multiprocessing, and then the master would sort of have a scheduler, and it would decide, hey, you know, it would have the function of synchronizing everything, managing everything. It would, for example, say, hey, you get this process and you get this process. So this is what asymmetric multiprocessing is all about. And obviously, in order for this to not go wrong, the processes also have to be sort of like well communicated, and everything has to be well communicated. And you have to sort of have some good, well, synchronization isn't really the good word, but yeah. So you have symmetric multiprocessing, and in that case, right? Well, the reason AMP seems appealing is you have a whole CPU dedicated to being a master and managing everything, and the slaves don't really have to care about all the processes being executed properly, because the master is, for example, going to handle the entire multi-level feedback queue, and it's going to hand over processes to the individual slave CPUs. Whereas in SMP, you sort of need to make sure that the CPUs are all independent. They know of all the processes states, so that two CPUs won't try running the same code, and similar things to that. So that's SMP and AMP, and yeah, about communication, about synchronization. I'll be talking way more about that in the next video, where I'll be talking about synchronization primitives. I'll be talking about threads and then problems that arrive and that could be solved with some synchronization primitives, such as the critical section problem, the deadlocks. But I will give a brief overview of IPC. So IPC is a term that refers to inter-process communication. So if I have some two processes P and Q, they could obviously want to sort of send a message to each other. There are two sort of basic solutions to inter-process communication. You could have some sort of buffering, or you have something which is a mailbox, or something well, akin to a mailbox. So the idea of a mailbox, right, would be that each process sort of contains its own region of memory where it would have messages related to that exact process. And then you would have some sort of function which would allow for a given process to send some data to the mailbox of another process, and the only thing it would need is the message that it wants to send, obviously, and the PID, the process ID of that process. And this, communication overall would work in a way that, for example, some process P could send to the PID of Q some message, and it could, for example, receive an acknowledgement. And that process, right, it looks at its mailbox, it has received some message, and it can, for example, send an acknowledgement, or not. There might be no acknowledgement. It all depends. But acknowledgements are also a bit more common in buffering. So the idea of buffering, right, is that you have some select region of memory which would be shared. And the processes sort of write different information without having to know the PID. Some process can write some information to the buffer, and then the other process can, for example, read the information from the buffer, and then it can, for example, write down an acknowledgement. Another process can read an acknowledgement. Most inter-process communication is made out of writing to some sort of memory, either that being a buffer with a specific address that will be shared between processes, or the sort of mailbox solution where it sends for the PID, and the operating system knows where the region of memory is that the sort of process can access. And so it's usually just sending this message and eventually maybe receiving acknowledgement. So that's inter-process communication. So there are many common signals that are used in IPC, and the sort of common Unix, there are like around 32 common Unix IPC signals, with probably, you know, something famous being, for example, SIG-SIG-B. That's a signal of a segmentation violation. So some memory segmentation violation has occurred. That's number 11. Or for example, kill, which is used to, you know, kill a given process. That's, for example, number 9. So you send some specific numeric identificator of some IPC message to a given process. And this sort of IPC is also related to synchronizing processes and such. But more about that in the next video. So yeah, I hope that, that's basically everything I wanted to cover in this lecture. I hope that it was a relatively good introduction to processes, you know, process sort of creation. So, you know, you take a program, you sort of parse it, you have, you know, all the different instructions, and you know, you have this process process control block, you have a PCB, you fill all the different information, you know, you have this, you have forking, you can have information about the children, the parents, you can kill processes, you can, you know, they're generally an active unit, you have to schedule them, you know, you have to perform context switching. This can be even done, this could be, you know, you have some preemption, you can yield the CPU time as a process, you know, each process can yield the CPU time itself. I hope this was a general good introduction to how processes and operating system work, how, you know, you can schedule user space processes, and there are more considerations related to that, more things that sort of arise from multitasking, having to deal with all of that, and I'll cover that in, I guess you could say, the second part of this lecture. But what I'm generally happy about is that I have covered the 4 main resources that I talked about in my first video, because we've already covered memory. Well, I think I've started with I/O devices, but it was memory, data, or well, the file system, right? And now CPU time. So now just more considerations to CPU time, and then another point from the first video that I also mentioned, and generally the series will be complete very soon, and I'm really happy about that. But also sort of not happy because, well, this year and a half have passed quite quickly. But also, I think it's good that I made this plan for something 15 lecture-ish, because anything more, I don't know if I would have finished it, but now I have this sort of motivation to actually finish it. But yeah, I hope that this was a generally good introduction to processes, scheduling user space processes, and I hope that we'll see each other in the next lecture.